In late 2026, the AI industry quietly crossed a threshold. We stopped building reactive chatbots that wait for our input and started deploying proactive agents. To do their jobs, anticipating our needs and managing workflows, these agents require continuous root-level access. They need the authority to modify system files and execute commands independently. But giving an AI that kind of power creates a massive vulnerability. We saw exactly what that looks like during the OpenClaw crisis of May 2026. Hackers figured out how to hijack powerful local AI instances using a simple hidden prompt injection tucked inside an ordinary external email. Once the agent read the email, the malicious instructions bypassed the local security sandbox. The hijacked AI started executing arbitrary code and silently siphoning private database blocks directly to remote command and control servers. It proved a harsh reality. Granting an AI agent the root access it needs to be useful automatically transforms it into an unauditable systemic liability. This exposes the trusted environment fallacy, the assumption that you can protect enterprise data privacy using software-level administrative rules or corporate terms of service. This diagram shows exactly why those software defenses fail. Traditional firewalls monitor incoming threats, but when a cloud-connected AI continuously talks to its host server, the firewall reads that massive outward data flow as legitimate, approved user activity. When an agent is tethered to a centralized cloud architecture, continuous data collection isn't a glitch. It is a structural feature of the business model. Corporate data governments can no longer rely on software policies alone. To achieve secure automation, privacy has to be mathematically and physically enforced at the hardware level. That physical enforcement is the foundation of DeReticular Sovereign Sentry hardware. These gateway systems are designed to run localized AI models inside a physically hardened, completely off-grid state known as island mode. This schematic breaks down the first tier of defense, an integrated trusted platform module, or TPM 2.0 chip. Every time the system boots, this chip measures and cryptographically signs the core software configuration, establishing a verified cryptographic anchor for the system kernel. If someone physically opens the chassis or tries to modify the hardware, that boundary flashes red. The hardware instantly locks the cryptographic keys, preventing the system from booting into a compromised state. But hardware locks don't stop someone with a stolen password or intercepted multi-factor token. To solve digital key spoofing, the system relies on radio frequency fingerprinting, or RFF. This graph illustrates the physics of RFF. Every radio transmitter on Earth has unavoidable, microscopic variations in its internal circuitry. When a device transmits, the Sentry gateway directly samples the analog signal to capture this distinct, irregular electromagnetic turn-on spike. That analog signature acts as a mathematical root of trust. Unlike a password, it is tied to the physical imperfections of the silicon, making it virtually impossible to replicate or clone over the air. Because this signature cannot be duplicated by software, it removes the primary vulnerability of stolen credentials. You cannot spoof the unique physical transient of the hardware itself. This creates an operational dilemma. You want the security of local hardware, but you still need heavy cloud computing, like Google's Project Remi, for complex reasoning. How do you use the cloud without exposing sensitive data? The answer is the split ledger architecture. It physically separates the private, raw, local data from a totally isolated outbound communication container. Here is how that works through a process called the digital airlock protocol. First, the local sandboxed AI agent takes a highly detailed private data block and extracts only the specific logical entities needed for the task. Next, the local agent aggressively scrubs all identifying metadata from those entities. Names, locations, and details are erased, leaving behind a generic, randomized token. Then, the firewall bridges only that sterilized token out to the centralized cloud. The external AI performs the heavy mathematical lifting without ever knowing who it's computing for, and sends raw logical vector coordinates back across the boundary. Finally, the local sovereign gateway receives those coordinates and maps them directly back onto the physical assets sitting safely behind the firewall. This pipeline guarantees that a local AI agent can leverage massive global intelligence without ever yielding structural control or leaking a single byte of corporate data. We can see the power of this setup in the industrial foreman deployment scenario, where hardened Sovereign Sentry nodes are mounted directly onto critical physical infrastructure. Out here, the local agent manages complex physical systems, like adjusting the tilt of massive agrivoltaic panels or regulating battery temperatures, completely off the grid. The agent issues logical directives to the equipment via industrial controllers. It translates digital math into immediate physical movement, continuously processing the site's telemetry with zero outward data exfiltration. By operating entirely locally in this island mode, critical physical operations remain functional regardless of centralized DNS poisoning, cloud harvesting, or global internet outages. Transitioning an enterprise or municipal facility away from vulnerable cloud dependencies requires a structured approach. DeReticular breaks this down into a strict 90-day deployment roadmap. The first 30 days focus on auditing existing local devices and mapping data vectors to expose the exact vulnerabilities lurking in the current network setup. The second phase brings the hardware on site. Physical Sovereign Sentry systems are deployed, and unique cryptographic keys are generated inside the TPM chips to lock down the local firewalls. In the final 30 days, the decentralized local network is synchronized. The specialized AI agents are loaded onto the hardware, and the facility officially activates its air-gapped island mode. Software-based security rules are easily bypassed by autonomous agents. Reliable protection now requires a boundary defined by the physical hardware itself.